For the exam 2. Exam 2 is all about thermodynamics. Now, the first topic that we haven't talked about in quite some time, but is actually kind of lumped in with this material here, is non-ideal gases. And for this, we have the virial equation of state, the SRK, the Peng-Robinson, and the compressibility factor. A number of different ways that we can use to solve non-ideal fluid systems. Now, non-ideal gases are basically non-ideal equations of state. This is relating between P, V, and T. Now, for the most part, what we care about is relating pressure and volume and temperature. Well, yeah, I guess all of these here, right? But in terms of process conditions, right? If this is its pressure, this is its volume, what is its temperature? This is its pressure, what's its temperature, and a volumetric flow rate. Now, in Thermo 2, you will use these equations of state to calculate enthalpies, entropies, internal energies, and all that kind of stuff, right? So the equations of state have a lot more value than just saying, oh, what's the density of the gas inside of the tank, right? That's kind of the most trivial application of it. But for what we're trying to accomplish in this class, that's actually what we care about for these circumstances, right? But these have a lot more power, right? People didn't spend, their lifetime developing equations of state just to better estimate the density of a fluid. It's much more important than that. Okay, so this kind of is our single phase discussion, but for the majority of what we worked on, it was multi-phase, multi-component. Multi-phase and multi-component. So what we started off on multi-phase, multi-component was humidity and saturation. Now, humidity typically refers to water in air. Saturation would refer to anything basically dissolved into anything else. So this could be how much vapor is in a gas phase. And for the purpose of humidity and saturation, that's specifically what we're talking about. But this term saturation is sort of a catch-all term that we'll use a lot, right? How much solid dissolves in a liquid, for example. Like, what's the saturation point of salt in water? Now, to do this, we did a simplification of Raoult's law. Oops. Right, we use this simplified form of Raoult's law, where normally in Raoult's law you'd have the x for the mole fraction of the liquid phase, but in this case we're assuming it's 1 because the gas is not dissolving into the liquid in appreciable quantities. So we can relate the amount of a liquid that evaporates into a gas phase based on this expression here, and then this of course is just the definition of the partial pressure. And within this subcategory, we had relative humidity and we had absolute humidity. So the relative humidity is how much vapor you have actually in the system compared to how much is the maximum amount for whatever temperature and pressure conditions you have. Absolute humidity tells you the physical mass of material that you have vaporized. Right, so these communicate two different pieces of information. Now, the reason why we care about relative humidity is because for evaporative processes, we don't necessarily care how much the total amount is in the air, but if we have 100% saturated conditions, we cannot evaporate any more material. So if you're operating a cooling tower or a swamp cooler, or you're hoping that your sweat cools you down when you're working out, right, 100% relative humidity is going to mean that it's not going to help, right? And that's why in Utah you don't realize, you're still sweating, like if you're going for a run in Utah versus going for a run in Florida, for example, right? But that sweat is just evaporating really quickly, and that's why you feel like you have salt caked onto your face, for example. But if you go running in Florida, your body's still producing that sweat trying to cool you down, but it's not going anywhere, right? Because the relative humidity is higher, which means that there's less of a driving force to evaporate. But the total amount of water in air, or some volatile species in air, that's given by units of absolute humidity. Now, I don't want you to lock yourselves into thinking this is, some specific formula. The key concepts that I want you to understand are relative humidity is how close you are to the saturation point. Absolute is the physical mass. But there's always a number of different ways you can report these units, right? You can do it on a molar basis, a mass basis, ratios, but the two main concepts are what I want to get across here. We talked about psychometric charts. Right, the psychometric chart is a really convenient, easy way to do humidity calculations. And they're typically built on a basis of dry air, which means that you can add and take water in and out to make it easier to work with. Psychometric charts are very useful for HVAC fields. So if you're designing heating and air conditioning systems. Now, when we moved up from here, then we talked about vapor-liquid equilibrium. And this is Raoult's law territory. So for every species, and this is Raoult's law, Raoult's law relates the liquid phase composition to the vapor phase composition. So if you know the temperature and the pressure, you can solve for the composition of the two individual phases. You don't know how much of each of those two phases you have until you add in a material balance. So under the category of vapor-liquid equilibrium, we talked about dew and bubble points, and curves. We talked about flash calculations. We talked about TXY and PXY, and this is ideal and non-ideal. And of course, the concept of vapor pressure is something that's really important to understand, what it means on a phase diagram. Let's see, anything else in vapor-liquid equilibrium? That's the most of it.
Could you define flash calculation?
Flash calculation? Yeah, so flash calculation is defining the liquid, the vapor. So a flash calculation, in this particular class, we refer to it as this liquid-vapor form of separation, right? Where you have a liquid coming in, you have a vapor going out the top, and another liquid stream coming out the bottom, and they should be different compositions. Now, the term flash is actually a generic thermodynamic term, meaning calculating the composition and quantity of each of the two phases. So in theory, if you were to go into a process flow simulation software, like you will in your senior year, Aspen. Who's heard of Aspen? Few people. So Aspen is the software tool that basically does everything we've learned in this class automatically. Right? So, but the downside is that when you're using Aspen, you don't just solve one process, you solve an entire integrated chemical plant. So it's actually a lot of work. Now, if you go into Aspen and you say, I want to use the flash tool, you could use it for liquid-liquid equilibrium, vapor-liquid equilibrium, solid-liquid equilibrium. Basically, what you'd be defining is you would say, perform a thermodynamic calculation on these compounds under these conditions and tell me the quantity and the composition of each of the two phases. That's a flash calculation generally. We treat it, though, for just the vapor-liquid equilibrium case because we don't have the know-how to go through and use it in more complex scenarios. So when we refer to a flash calculation generally, we're asking for the composition of the vapor, the composition of the liquid, the total amount of liquid, the total amount of vapor at some temperature and pressure. But you could also imagine working this backwards. If you knew the total amount of liquid and vapor, maybe you could solve for the compositions. Or if you know the compositions, you could solve for the temperatures and pressures. Everything is a function of everything in thermodynamics. Right? So we're not always necessarily going to be giving you the temperature and pressure. You might be solving for the temperature and pressure in order to satisfy Raoult's laws. Right? But thing to remember, Raoult's law tells us the compositions of the two phases. for vapor-liquid equilibrium. And we spend most of our time on this topic here because it's an equation that we can actually use to solve and develop our own phase diagrams. Now then, when we transition over to some other topics, the next subject was liquid-liquid equilibrium, LLE. And for here, we talked about a triangle diagram, a liquid-liquid extractor, you know, what does this process diagram look like? How does it operate? Sort of what are some of the terminologies and definitions? We also use something called the partition coefficient. Partition coefficient. And then lastly, we kind of lumped everything else into just other types of equilibrium calculations. And specifically, we talked about solid-liquid equilibrium, how much solid dissolves in a liquid. But the main thing that I wanted to introduce in this topic was just understanding that when we say something is saturated, that's the maximum amount. You don't have to be fully saturated. And in fact, for almost all chemical processes, you're not going to be fully saturated because it takes too long to get to that equilibrium point. Equilibrium is infinite time. So generally speaking, you never reach saturation unless the diffusion is really quick, but we'll use it as a design tool. Yeah, question?
So is relative humidity just, never mind, that's really stupid. It's the same as relative saturation.
Yeah, so it's the same thing except humidity we use for water and air, saturation is the more general term. So in essence, the term humidity doesn't need to exist, but it's just convenient because we deal with water and air a lot. Yeah.
And then regarding absolute humidity, so you could just take the mass of would it be H2O in that case, and you can just divide that by the mass of the air to know the absolute humidity. Is that how that kind of works?
Yeah, so the absolute humidity would have units typically and I think the Felder book differentiates between these two, but it's really just a unit conversion issue. But I would think of absolute humidity as grams or mass of water per gram of air, or grams of water per gram of dry air. Now I think the Felder book might differentiate between one of these as maybe the humidity ratio and one's like the absolute humidity. But I kind of think of this as the same concept, just with two different bases. Right? This is a basis of dry air, water-free. This is a basis of all of the air. In general, this is probably going to be the more useful, the amount of water per basis of dry air. But translating between these two is just a simple unit conversion material balance. So I hope this is not an intimidating or confusing part of it. Yeah.
So would the dry air just be the equivalent of air in this case?
It would be all of the air minus the water. Same thing like when we did the dry basis versus the wet basis on combustion effluent streams. So same concept here. So dry air would be just the oxygen and the nitrogen. Air would be the oxygen, the nitrogen, and the evaporated water. So it's just two different bases.
And you would mostly want us to use the H2O over the dry air then?
That's probably the easiest one to use. Yeah, because you're in any sort of a gas phase process like that, you're not going to be changing the composition of your air. And so you can hold on to that as a constant that's going to be just flowing through your system. And so if you're operating, let's say, a dehumidifier, you're going to be dropping out the water, but you're not going to be changing the air flow rates. So it's just easier to keep the dry air basis as the one that you're working with. In, for example, something like a humidifier or a dehumidifier. Okay, these are the general topics that we went over. Question?
Yeah, could you explain what the partition coefficient is? Because I don't remember.
Yeah, so let's start assembling a list of topics to cover. So we have partition coefficient. What else? Yeah.
There's on the things to know page, there's calculating the volumetric or molar flow rate to a corresponding standard temperature expression.
Okay, so that would be applying a equation of state, right?
Yeah.
Okay, so let me see. So let's call it n dot to v dot, I guess. Is that the question?
Let me read it.
Translating, okay.
Let's see. Convert a flow rate, either molar or volumetric, to the corresponding flow rate at a standard temperature. So would you be given like a different?
Okay. Yeah, that's a pretty trivial one.
Okay.
That one's just the STP conversion.
Okay.
So, for example, if you have a pressurized natural gas, they'll often buy it in standard cubic meters worth of gas. And for there, that's just a unit conversion of 22.4 is what it is, I think? Yeah, that's as simple as that one.
Okay.
Yeah, that's all that one means to say. But in general, if you were to do this approach where you're trying to go from a volumetric flow rate to a molar flow rate, or vice versa, then this would just be the application of an equation of state.
Okay.
Right, so that's just ideal gas law, or you could use a more complex equation of state. Okay, what other topics do you want to cover?
Can you go over crystallization again?
Crystallization?
Yeah.
So that would be like solid liquid equilibrium?
Yes.
Yeah, that one is it's essentially the same.
Okay, what else? There were more suggestions earlier.
Compressibility charts.
Compressibility, so Z equals PV over RT. Okay, what else?
Relative humidity.
Relative humidity. What else? Everyone feels 100% confident on TXYs and PXYs for ideal, non-ideal.
If you could go over non-ideal, just on, just parts of it.
Okay, so non-ideal VLE. Triangle diagrams, everyone's okay with triangle diagrams too?
Can you go over the sections?
Okay,
Yeah.
fine.
Well, I just want to
Okay, so what, let's do, okay, let me see here. Let me do partition coefficient and triangle diagram at the same time and talk about liquid-liquid extraction so we can take 2 things off the list. So this is liquid-liquid extraction. First step. Let's say you sit down, you're nervous for the exam, you open it up, and the first question is on liquid-liquid extractors. How would you draw the process flow diagram?
You'd have 2 streams going into a process and then 2 streams coming out.
Bingo, 2 streams in and 2 streams out. Now, if we were to visualize this, how this would actually be operated is you would find a way to bubble one phase through the other to maximize the contact in the surface area because you want the solute, right? And typically in a liquid-liquid extractor, let's draw this out in a triangle diagram. Typically you have 2 immiscible phases on the bottom, right? And this is just sort of a standard convention. We'll just call those phases A and C, and B is the solute that you're trying to collect. So generally in a liquid-liquid extractor, you're going to try and get the B to go from one phase to another phase. And that's how you can concentrate it and make it easier to separate and extract. So here we might have A plus B and then pure C going into the system. And then you mix the 2 together the best you can, and then eventually they settle out into 2 separate phases, and then you literally have just sort of like a plate that separates the 2 the best you can. And you'll have A plus B plus C and A plus B plus C. Now one of these 2 phases is going to be what we call the Enriched Phase. And this is going to be the C-rich phase. So if we draw a phase envelope in our triangle diagram, if we're operating our separator well, we should be in this 2-phase region. Otherwise, you just mix it together and you have a homogeneous fluid, right? This is the 1-phase region, this is the 2-phase region. You'll have tie lines that connect from phase 1 or phase 2. Now, what you call phase 1 and phase 2 is totally arbitrary. So typically it's better to call this the A-rich phase. There's more A in this phase, so we call it the A-rich phase. And this one here, we'll call this one the C-rich phase, because it's closer to the C axis. And then, of course, you can read these values off, and you can know the composition here, composition there, and you can do your material balances to solve for the process. Now, you could have multi-stages of a liquid-liquid separator, where then you could add even more fresh C to this compound here and try and get more out of it. Right? That's a multi-stage separator. Now, the partition coefficient K is going to be equal to the mole fraction of B in some phase 1, or the mass fraction, it depends how it's defined, compared to the amount of it in the other phase. So in this circumstance here, if this K is greater than 1, that means your solute B wants to be in phase 1. If your K is less than 1, that means your solute wants to be in phase 2. So what this basically is a simplification of taking down this whole triangle diagram and basically grabbing your mole fraction or mass fraction of B of each of these two phases here. Right? So in theory, you could look at a triangle diagram and calculate your partition coefficient. Yeah.
And you said it's, so for the A-rich phase, so if it's the mole fraction, would it be, so it'd be like A over the total for the A?
It would be A over the total, yeah. So in this case here, right, if you remember how we read these, you have the lines going across, right? So this one here for B might be, I don't know, let's say 10%.
Okay.
Right? Let's just say, for example, this is 10. So this would be 0.10, right? That's the mole fraction of B in this phase.
Okay.
Over here, let's say this is 25%, 0.25. So in this case here, if we looked at this triangle diagram, we would develop that partition coefficient. So the partition coefficient is a simplification of using the full triangle diagram approach. Question back there.
So is there any standard about which one goes on the top and which one goes on the bottom when you're using it?
I think the standard typically is the B is going to want to be your co-solute, the one that's miscible in both A and C. Most of the time when I see a triangle diagram, it's the two-phase region is on the bottom. But sometimes you'll find that you'll have another two-phase region like that as well.
I don't think that's what I meant. When you're using the partition coefficient, like they give you a number of like 1.27, is it always going to be like phase 1 over phase 2, or?
It's arbitrary what you call phase 1 and phase 2. Yeah.
Okay, that's also not.
Yeah, but I think typically you'll want to write your partition coefficient so it's a number greater than 1, I think, so that whichever phase you put on top is the one that it wants to be in. But sometimes you might not necessarily know.
Okay, so
But the idea behind the partition coefficient, it's the ratios of the mass fractions. So it's the concept, it's a little bit funny because it's a mass fraction over a mass fraction, so it's a unitless quantity over a unitless quantity that gives you a unitless quantity, but it's really just a way to package the information in a compact way. Does that help?
No.
Okay.
So, if you have your liquid extractor,
Yes.
you have the one that's on the top and the one that's on the bottom, right?
Yep.
So you have the amount of the B that's on the top and the amount of B that's on the bottom.
Yep.
Is there any, like, is it always going to be the phase that's on the top over the phase that's on the bottom, or is it like sometimes going to be like the mass that's on the bottom over the mass that's on the top?
That will depend on the density of the fluids. So in terms of convention, why do I call this one phase 2 and this one phase 1? Would this one always be on the top and this one always be on the bottom? So for the material balance purposes, it doesn't matter how the process is actually operated. But in reality, when you have a liquid-liquid extractor, one phase will be more dense than the other, and that's will be the one on top and on the bottom. But in terms of how you actually construct this process, for the purposes of how we solve and balance it, it actually doesn't matter. Which phase is on top, which is on bottom, what we call 1, what we call 2. Because how you would actually operate this is you would take the less dense fluid and you would actually feed it into the bottom so it would bubble up through the more dense one and they'd mix together and then they would resettle and then flow out again. But in terms of, for our purposes, it's probably easiest to keep, the A-rich on top and here and the C-rich on top there. So how we're drawing it is not actually how it's going to be operated. And the convention here, if there is a convention, I'm not aware of it.
Okay.
But the key thing is just the ratios of the mass fractions. Yes.
So maybe this, so will it, if you're given a partition coefficient, will it specify what the ratio is, I guess? So it'll say Enriched Phase. So it'll give you the partition.
Yeah, it'll give you the definition of
and
how the
say-
partition coefficient is defined,
Okay.
and then you have to unpack it.
Yeah.
So, the key thing here is how do we apply the partition coefficient to get
Yeah.
variables that we can see and understand in our material balance. Right, so if we were to rewrite this here, let me get rid of my junk math. And so if we were to rewrite this, right, this would be the mass of B in phase 1, which would be this stream here, let's say for example. We'll call this phase 1, and we'll call this phase 2. Wait, yeah, I got that right. Divided by mass of A, phase 1, plus mass of B, phase 1, plus mass of C, phase 1. Right, and then same thing down here, mass of B, phase 2, divided by all the individual things for phase 2. So the key thing is the partition coefficient is just basically a design specification. So if I just gave you this equation, you could see how you could manipulate it and say, oh, I need this one for this material balance and this one for that material balance. Yes?
Is the triangle diagram set up so the partition coefficient is always constant when you're on a timeline anywhere in the two-phase region, or does it depend on the initial composition?
That's a good question. The partition coefficient, if you're on a tie line, will be the same for those conditions. Now, the partition coefficient, though, is a simplification. Because these tie lines, they fan out a little bit. So if I'm here versus here, you're going to have slightly different partition coefficients. So the assumption that you're working with is sort of that the ratio stays the same regardless of the condition that you're in. And so the partition coefficient is going to be a simplified way to solve the problem, whereas the triangle diagram is going to be more close to the actual conditions. But the problem with the triangle diagram is that it's not an equation, right, that we can put into a solver and we can just solve explicitly. It's looking up data. And so if you're trying to solve something that's not a simple, straightforward problem, using the triangle diagram means you have to iterate, like guess and check approaches with charts, which is not super pleasant. So partition coefficient might be a simplification that you could use to start off with. But you could, in theory, right, you could calculate a partition coefficient for all of these different tie lines and then calculate an average, and then maybe that's an easy way to solve problems at early stages for a process design.
So they do vary, it'll be different for every timeline.
They should, a little bit. I don't know how consistent it is for a typical liquid-liquid triangle diagram. Yes?
And just to ask about the partition coefficient, so if it's greater than 1, you said you're going to be in the phase 1. You have more.
Yeah, so let's just look at it for a second here. So we're dividing two mass fractions. So if the mass fraction of B in phase 1 is bigger than the mass fraction of B in phase 2, K is going to be greater than 1, right? Big number, small number. It's going to be greater than 1, which means that the B will want to be in phase 1 versus phase 2. But the partition coefficient, right, is just an approximate way to solve these problems with a relatively straightforward unit. But it's kind of a weird unit, right, because it's got two mass fractions here, but then you actually end up having like 6 different variables when you actually unpack it.
Thank you.
All right, so partition coefficient triangle diagram. Any other questions on those topics before we select our next review material? Let's march through in terms of what we covered. Let's talk about the compressibility chart. Is everyone okay with calculating volumetric flow rates using, let's say, the ideal gas law? Everyone's okay with the virial equation of state and the more advanced ones? You have a question on the virial? You won't need to know them, but you'll need to know how to apply them. So I'm not expecting that you can bust out, the van der Waals equation off the top of your head, right? I'll give you the equation, I'll give you the A and B coefficients, and I would want you to execute the equation and figure out how to get the answer out. So knowing how to put everything in the right place, like, what is the critical point and critical pressure, all that kind of stuff, how does that go into the calculation? That you'll need to know, but you won't need to memorize the actual equation.
So
Yeah.
we don't need to worry about writing that on our equation sheet?
No, unless it's a, I don't know, a Zen-like experience for you. No, but any advanced equation of state I will give you. I won't give you the ideal gas law. That one I'm expecting that you'll have committed to memory. But anything else, right? You shouldn't need to have. Like, my goal is that you shouldn't need the equation sheet at all, because ultimately for this exam we have equations of state and Raoult's law. And apart from that, it's all really concepts and how we apply those. And Raoult's law is an easy enough equation to commit to memory. So really, you shouldn't hopefully need to use your equation sheet at all if everything is really rock solid. But obviously, you could maybe pre-solve for bubble and dew equations. But those are also something you can fairly readily commit to memory. Yeah.
So, most of the stuff from the last homework is not going to be on the exam? Like the
Energy balance stuff, no. No. Energy balances, no. That'll be committed for the third and final midterm exam. So this is we're gonna try and chop it off before we get to the energy balances. We've got plenty to talk about with phase equilibrium, but we will go backwards, of course, right? So material balances are of course fair game. So everything on exam 1 is fair game, but the emphasis is going to be on multi-component, multi-phase. But a liquid-liquid extractor, we cannot solve this problem without knowledge of material balances. A flash separator, we can't solve that problem without material balance knowledge. But generally speaking, it's going to be non-reacting material balances. But it's possible we'll have multiple unit processes. Absolutely we have to have material balances, unit conversions. So exam 1 material, fair game. Same thing moving forward when we go to exam 3, you're going to of course have to know multi-component, multi-phase equilibrium. Right? Because one of the key aspects is going to be calculating an energy balance on a flash separator, for example. So that's going to be material balance, energy balance, phase equilibrium calculations all wrapped into one. All right, compressibility chart. Okay, so compressibility chart is one of about 4 ways that we talked about to estimate the properties of non-ideal gases. The purpose of the compressibility chart, or all the other calculations, is that now I no longer have to provide the mass flow rates in and out strictly as molar flow rates. We can talk about volumetric flow rates. Sometimes it's easier to purchase or think in terms of volume, right? You're buying a gallon of acid. You're buying, a standard cubic meter of natural gas. And so we have to convert those volumetric flow rates to molar flow rates in order to, actually we need this little hat right here, in order to implement them into a material balance. So the compressibility chart, if I can draw this right. So on the x-axis we have the reduced pressure. This is defined as the system pressure divided by the particular fluid's critical pressure. If you have a mixture, we calculate something called the effective critical point. I put a little prime right there, which would just be a mole averaged critical point of all the individual species. Same thing applies for the effective critical temperature. And these are just mixing rules. And it's an approximate way that we tackle these things. On the y-axis, we have our compressibility chart, compressibility factor. All right, there is no n in this equation. That is lumped into the density or the specific volume, depending on however you want to think about it. So PV over RT. And on the chart, we have a series of lines. And I don't know if I'm representing this very well, but hopefully well enough to illustrate the concept. These individual lines correspond to specific reduced temperatures. Now the chart can be used in a number of different ways. The most straightforward application is if you're given temperature and pressure and you want to calculate the specific volume of the fluid. That's going to be the most straightforward application of the compressibility chart. But of course, you can work backwards. You might have to iterate or guess and check, but you can do it. So the general procedure in order to get from a temperature and pressure of a particular fluid to its density or specific volume is we would first calculate the reduced temperature, the reduced pressure. Once we know what a particular reduced pressure and reduced temperature is, we can lock ourselves into a particular position on our compressibility chart. Then we can read off the compressibility factor and use that information to calculate the specific volume of the fluid. Now let's say we wanted to work backwards. Let's take a second and think about how we would accomplish that. Let's say we want to go this way. We have a specific volume, and we want to figure out at what's the pressure. Let's say we know the temperature. We know the temperature, we know the specific volume, but we don't know the pressure. So the problem is, it now becomes an iterative approach, because we need to know what Z is and T is in order for us to figure out what the P would be, the pressure would be. But it's totally doable. If we know the temperature, we can calculate the reduced temperature. Let's say it's this line here. So we're somewhere on this line. The problem is we don't know Z and we don't know P, because there's pressure in both of these two expressions. So you would effectively have to find some point on this curve where the pressure satisfies the Z that you're given for this particular volume. Does that kind of make sense? Because the pressure is in both terms. So I would guess a pressure, calculate its reduced pressure, see where it falls on the line, see if it matches with the Z that would be resulting from that particular specific volume and pressure. Sure, why not? Right, but it's just like the psychometric chart as well. If you know two things, you've fixed the position. It's a little bit trickier because it involves a little bit guess and check work, but the same holds true. Yeah.
So would you know your Z, your compressibility value then, if you know the specific volume then?
You would not, because you need to know your pressure.
Oh, sorry, yeah.
Yeah, so you would guess, so in this particular instance, you would guess a pressure, you would calculate PR, you would calculate Z, and see if your conditions match. They all line up on a single point on the chart. But you could use this backwards, right? But the conventional approach is you're given temperature and pressure, and you're calculating the volume. All right. How do you feel about the compressibility chart? Yeah.
I have one question. Is that a P prime C and a T prime C?
Yeah, this would be for a mixture.
Okay, and so what does that stand for?
I just put the prime on there to let it be known that it's not the actual critical pressure or critical temperature.
Okay.
And so then, for example, you would calculate a P prime R for the mixture. And then that's what you would put into the compressibility chart.
Okay.
So you're calculating an effective reduced pressure or an effective reduced temperature based on a mixture.
Okay.
I think they call it K's rule. That's what this is called here. And some of these rules, they're just empirical rules that seem to work well enough that no one bothers. Yeah.
So on the practice test, one of the questions, you had like a balloon and it got reduced to a certain pressure. Like, how do you know which like temperature and pressure to use? Like we're given 4, and then you give us the TC and PC.
4 degrees C. So
like it's at like 100 degrees C, and then it goes to 4 degrees C.
Sure.
So which temperature would you use to calculate your TR?
So in that particular instance, so if we took, I think in that one we took a balloon and we pulled it all the way down to the ocean floor and then figured out how much water condensed. Is that the problem?
Something like that.
So it depends on what condition you want to solve for the specific volume for. So at 100 degrees C, you would calculate the PR and TR, and that would tell you the density of the fluid before you submerged it into the water.
Okay.
at the end, at 4 degrees C, and whatever the pressure is, you could calculate it for the final conditions.
Okay.
So if the temperature's changing, that means everything else is changing. That means your Z would be changing. And so you have to fix everything at some point in time and space, and then you can calculate all the properties. But you'd have to choose for one of those two situations.
Okay.
So they would have different specific volumes.
Okay.
Yep. Okay. Let's see. Okay, we did this one. No, we did this. Compressibility chart. Now let's talk about. I'm going to lump in solid liquid equilibrium and relative humidity because it's the same concept. So, let's say, for example, just intuitively, is this room 100% saturated? How do we know? How do we know it's not 100% saturated?
The relative humidity is 100%.
Right, but we could feel if it's 100% saturated, right? It would be super muggy. It would feel like the air was thick, right? We've all been in really humid environments before. But the question I have is, if I were to open up my cup of coffee and just let the water molecules evaporate, or if everyone opened up all of their water bottles, is it instantly saturated? Well, Raoult's law predicts that it should be instantly saturated. Right? So Raoult's law only tells us the conditions at equilibrium. But the instant that I open my water bottle, all the water doesn't instantly evaporate and fill the room up. Right? So the relative humidity tells us what the conditions actually are. Raoult's law tells us what the theoretical infinite time limit would be. So yes, if we had a bucket of water sitting in this room and we sealed everything up so no air could get in or out, after a while, yes, the room would be 100% saturated. But it takes time for the water to evaporate. And so in the atmosphere, this is not an equilibrium process. It's a dynamic, non-equilibrium process. Right? Dry air is blowing across the desert. Maybe it picks up a little bit of moisture going over, the Great Salt Lake or Utah Lake. Right? That's what's determining the humidity in the atmosphere. How much is it pulling from the grass and the plants? But it doesn't mean that it has to be 100% saturated. So the relative humidity I view it as the mole fraction of water divided by, and I put this star notation here. And in class, I tend not to use this very specific notation because I don't want you to think that this concept is just a simple mathematical relationship. I really want it to be clear that Raoult's law is the infinite maximum equilibrium. But here, Y star, I can write as the saturation pressure. I call it P star always, right? Right? This is just a rearrangement of the one component Raoult's law. So in the homework solutions, I have this relationship right here. This is the actual amount of water in the air divided by the theoretical maximum, which is provided by Raoult's law. But in class, I never use this sort of star notation because I really want this not to be an issue of just knowing that, oh, we're solving for Y star and not for Y. Right? The key thing to remember is that Raoult's law is infinite time, equilibrium, nothing's changing anymore. But it doesn't have to be to that point. And you can typically, it's in terms of percentage, so we could times it by 100 to make it a percent. So if I tell you that the room is 30% saturated with water, you would first have to solve for what the theoretical maximum is, then use the 30% to figure out what the actual mole fraction of water is. Then once we know what the mole fraction of water is, we could simply change the basis and convert it to an absolute humidity. And that's something that we all did on the homework, right? Houston conditions versus Arizona conditions versus Utah conditions, right? What is the actual amount of water in the air? So if I wanted to condense all the water in this room, how big of a jar would it fill up? That's an example of how we would use the absolute humidity to do a material balance to figure out how much total water is in this room. Maybe that's a good exam question, right? How much water is in this room? but that's just, all that is a material balance, right? It's a material balance. Once you know what the mole fraction of water is, all you need to know is what the total volume of the room is and how you can convert the total volume and the temperature and pressure to the total number of moles. Right, so it's just material balance and unit conversions beyond that point. Now, solid-liquid equilibrium is exactly the same concept. In general, we don't know a good universal way to predict the solubility of, let's say, a salt or a sugar in water. So instead, what I would communicate to you guys on an exam is, this is the saturation point. Saturation means 100% relative humidity. But in the case of salt dissolving into water, right, I'm just going to tell you this is how much mass. This is the maximum amount of mass that I can dissolve into that system. And if I say I'm 20% of that, or 10% of that, or 70%, it's the same concept here as relative humidity, except it wouldn't be the mole fractions. It would be whatever units that I communicated it in. Right? But that's the whole concept, is that all of these thermodynamic calculations, they tell us the infinite time equilibrium conditions, but that doesn't mean it's going to be the case. Same idea as if I took a sugar cube and I dropped it into cold water. Yes, eventually most of that sugar is going to dissolve, but man, it certainly helps to stir it around and break it up. Same idea as if you opened up your water bottle in the classroom. Not all of the water is infinitely going to evaporate infinitely quick and saturate the room. Right? So in your junior year class, that's where we go through the details of saying, okay, how do I actually design this chemical process to get me as close to equilibrium as possible with as little process equipment as possible? Here, we're working in fantasy land, and we're just saying, oh, magically we're making it to equilibrium. But that doesn't tell us, in heat transfer, we have to figure out how big are the pipes, what material should the pipes be, how thick will the walls be, what's the flow direction. In reactor design, am I doing this in a CSTR or a PFR? If I'm doing separations, what kind of a bubble cap should I have in order that I contact liquid and vapor together? Right. So all of the junior year curriculum is based on one simple concept: how can I get to the ideal calculations in this class by physically building a unit with pipes and flowing fluids? That's basically the entire junior year. The entire senior year is putting it all together and building a big chemical plant where not only do we do the big scale material energy balances like we were doing in this class, but also the nitty-gritty detailed design of where should I input this flow line, where should I take out that flow line, how should I design this unit operation. So it's a lot of work to get to that one end goal. Okay, now the last thing, let's see, we covered a good chunk of them. Let me just go over non-ideal vapor-liquid equilibrium quickly one more time. Now I have, I'm going to say very good videos on TXY and PXY diagrams on my YouTube channel. They are some of my most viewed content. I'm going to do a non-ideal PXY diagram really quickly right here. So help me draw this out. Should I draw on the right side, species 1 is my more volatile. Should it be high or should it be low? It should be, let's think about this. At high pressures, I should be in which phase? Liquid. At low pressures, I should be as the vapor. So the more volatile the species is, the more it wants to be a vapor. So we'll make that vapor region larger. Okay? And the less volatile species will be here. So the ideal conditions, I'll draw them as dashed lines. Which curve is this? Bubble. We know that because it's a straight line. And here we have the dew curve. How do we know it's the dew? We're going from vapor to the 2-phase. This is the bubble because it's liquid to the 2-phase. Right? Now I can draw any arbitrarily silly phase diagram from this point onwards. Right? Sure, something like this. This could totally be a real system. Which curve is this one? Still the dew. How do I know it's still the dew curve?
Because it goes from vapor.
Because it's the one that's touching the vapor, right? Vapor going to 2-phase. This is the bubble curve, liquid going to 2-phase. How do I know the composition of the system, right? Remember, Raoult's law relates between the composition of the liquid phase and the composition of the vapor phase at a constant temperature and pressure. This phase diagram is a PXY phase diagram. Which variable is held constant? Temperature. So no matter what, temperature being held constant is satisfied. How do I make sure the pressure is constant? I draw a horizontal line. So now I have fixed the pressure and I have fixed the temperature. I have two interesting points of intersection on my diagram. The point where my constant pressure line meets my bubble curve, this gives me my liquid phase composition. The point where my constant pressure line meets my dew curve, this gives me my vapor composition. So you should know how to generate TXY and PXY diagrams and also how to read them. But just because the curves look funky and non-ideal doesn't mean that the rules to analyze them are any different. Right? Constant temperature, constant pressure, that fixes my composition. Now, the difference here is that my total composition can be anywhere in between these 2 points. All that I'm controlling at that circumstance is how much of the liquid phase and the vapor phase that I have. And you could solve that according to the lever rule. Now, we didn't talk about the exact details, but there's videos online for the lever rule. But instead, my general default is just to do a material balance. For the simple reason of that's one less thing I have to know. Right? I know how to do material balances. I don't remember the equation for the lever rule off the top of my head. So unless I sit down and specifically look it up, it's going to be a bit difficult. Now, one thing that I will say about the lever rule is it will potentially give you more accurate results depending on how bad you are at reading the charts. Right? So if you're bad at reading charts, you're like, oh, I think this is 0.7, 0.7, and this is 0.8, right? Which is obviously wrong. Right? So if you read the charts really badly, and then you put that into a material balance, you're going to get a really bad result. Right? But with the lever rule, right, it's not as dependent as propagating errors, right? All of the errors are kind of lumped into how well you can read things on a ruler. So yes, there is a time and a place for the lever rule, and maybe I don't give it a fair shake in my daily life. So the lever rule will give you slightly more accurate results if it's a crazy non-ideal diagram that's hard to read. But if you can read the diagram really well and then implement it into a material balance, it should give you a pretty good estimate. Yeah.
And then you're able to calculate the vapor pressure of, like, say,
Yeah, the vapor, you don't have to calculate it, it's right here. And right there.
Oh.
This is the vapor pressure of species 2. This is the vapor pressure of species 1 at whatever temperature the diagram is made at. Right, you don't even have to calculate it, it's right there on the diagram for you.
And for TXY, it's the same orientation. You're going to have one up.
TXY will be flipped, right?
Yeah.
Because the more volatile species want to be in the liquid phase, and then the more volatile species want to be in the vapor phase, and the TXY, the vapor phase, is on top, so you want to make that one bigger. Does that kind of make sense?
So species 1 would still be down
In the
here.
TXY, you would start down here.
Right.
Right. And then up here for species 2.
Sorry, and the max pressure would be, to calculate max pressure, how would
The max pressure of the two-phase region, that would have to be for a particular composition. Right? So if you drew a vertical line here, this would be the max, that would be the min. This would be the bubble point, this would be the dew point for a particular composition. So, one second. Okay guys, see you on Friday, office hours today, office hours on Thursday. All right.